Well, thanks a lot, Zvi, and thanks to all the organizers for inviting me to talk on this great day. Very inspiring talks already from Sergey and Nathaniel. And I would like to tell you about some aspects of AI for theoretical physics, where I'll start off kind of broad, which might mean a little bit of overlap with some of the things Nathaniel told us, and then I'll dive into some more specific areas where we have some needs that seem like they could be fulfilled by AI, and people are working on aspects of that, but there still seems like much room for improvement. And part of it will also be discuss a specific project that I've been engaged with Kyle here and a number of other individuals to try to understand some collection of theory data that we have. So we know that particle theory is very reductionist in nature. Instead of looking for emergent phenomena, as Nathaniel said, we want to understand the fundamental microscopic dynamics and to organize phenomena at the most elementary level into particles or forces or whatever description sort of minimizes the set of rules or maximizes the number of predictions. And historically, this kind of thing has been going on for a long time. So there used to be separate phenomena of electricity and magnetism that were unified into electromagnetism. And then with the advent of relativity and quantum mechanics, and that was combined with electromagnetism into the field theory called QED, which essentially is the theory needed for most macroscopic terrestrial phenomena, except for gravity. And then with the weak interactions, this same framework could be enlarged, where we have a continuous Lie group, SU2 cross U1, where the U1 essentially includes the electromagnetism, and the SU2 corresponds to the exchange particles, the weak interactions, and those become electroweak theory. And then around the same time that SU2 cross U1 was being developed, it was understood how to write a similar theory with the unitary group SU3 for the strong interactions, which is a generalization of QED called quantum chromodynamics. And now we have this very successful standard model, as Nathaniel mentioned, which is built off of a similar set of principles involving this combined group. So the standard model has a Lagrangian, which can be written on a coffee cup available at the CERN canteen. And it combines special relativity, quantum mechanics, a particular kind of symmetry called gauge symmetry, into a description of nature that works remarkably well. It cannot explain the 750 GeV excess. Fortunately, that went away. Unfortunately for the standard model, I mean. Unfortunately, perhaps for us. And it explains essentially all terrestrial experimental results. We don't think it's satisfactory. That's why there are many attempts to go beyond it, both theoretically and experimental searches, which should probe for things beyond the standard model. We already have several pieces of evidence beyond the standard model. For example, neutrino masses do not really fit into the basic standard model, but there's one way which they can easily be accommodated. Might not be correct, but it seems to be consistent with all neutrino oscillation phenomena. We also don't have any particle in the standard model that can make up dark matter. And of course, dark energy is a separate phenomenon heavily linked to gravity and is similar to the early universe idea of inflation. And gravity can be added to the Lagrangian. We can make everything generally covariant, but at the level of point particles, it doesn't give us a very predictive framework for predictions at very high energies where we have difficulty building experiments. String theory is a theory of extended particles, which does unify quantum mechanics and gravity, but extracting specific predictions from it is a challenge for things at observable energies. So there are also many arbitrary parameters in the standard model. And that could be an avenue for AI. But humans have already created, as Nathaniel mentioned, many theories that try to predict these parameters. And it's hard to tell which ones are right without more experimental information that goes beyond the standard model. And finally, we have the seeming fine-tuning of the electroweak scale relative to the higher energy scales in nature, like the Planck scale, or even the scales that are being reached now at the Large Hadron Collider. Now, a big problem is that the standard model is a kind of closed theory, which is quite consistent. And there's no smoking gun that is solid experimental deviation from the standard model that tells us where to look next for things that we can couple to strongly enough to do reproducible terrestrial experiments. For example, dark matter, we don't have any lower bound on how it interacts with particles of ordinary matter to make it possible to see something about its interactions that are non-gravitational. So in this situation, there are several things theorists can do. And well, this is just my personal categorization, but people can certainly describe it different ways. And one is kind of along the lines of the last part of Nathaniel's talk, which is to propose new frameworks and models that lead directly to new experimental tests or to explain anomalies, for example. So to understand the space of possible theories that are consistent with all the data that we have that and to understand what's going on there. But there are other aspects of theoretical particle physics jobs. One of them is to understand what are the consequences of the standard model. So as I'll go into in more detail, we get this data from the Large Hadron Collider. But in some cases, you need to know what the standard model predicts in order to interpret it and check consistency with its predictions. And so I'll discuss that later in this talk. And then there's also the idea of searching for new principles by studying structural aspects of observables, like how particles scatter off each other, for example, in the standard model and related theories. And of course, none of these live in isolation. They're all connected to each other. And then the question, of course, is how will AI assist? So a lot of problems that you have in computational theoretical physics, they're limited by your computational resources and by the framework you've chosen to use. But there's obviously, or it seems clear that there are ways to optimize these problems. Some cases more obvious than others, but there are many computational tasks where it seems clear that AI will assist greatly in the future and is already starting to be used in similar ways. So another thing to do is symbolic regression. If we can generate a large amount of theoretical data, maybe we can find patterns in it that we can then interpret in terms of finding dynamical reasons for those patterns. And of course, and probably the one that has been very sort of profitable in the near term, there have been LLMs assisting with more and more complex tasks. And at some level, we expect that these LLMs and perhaps other more custom architectures might start thinking like physicists, whatever we mean by that. There's different levels of tasks, like there are different levels of mathematical problems. And of course, at some stage, we expect that some of these LLMs will perform roles that are those of practicing physicists. And of course, there's always the issue of how will the AI assistants be through the commercial LLMs like ChatGPT that are being developed versus more custom architecture for specific sets of tasks. And that might depend on the problem. Here's one clear example, which was mentioned also briefly by Nathaniel, and I won't go into too much more detail, but there are areas of theoretical physics where you're interested in exploring the complete set of possibilities. Instead of looking at the consequences of a particular theory, you want to ask, what are the bounds that we get from very general principles? And one such program is called the S-matrix bootstrap. And so it utilizes 3 different principles. So you have, it's often implemented on the scattering of 2 particles into 2 particles. And you can use the analyticity of the dependence of this scattering on the different energies and angles. Also crossing symmetry, which happens when you think about moving one particle from the final state to the initial and vice versa. And then unitarity, which is just a statement that probabilities should never exceed 1. And these constraints, especially the unitarity constraint, can often be nonlinear. It can require knowledge or input of somehow of higher point scattering, like 2 goes to 4. And so when the constraints are implemented in a nonlinear way, that is where it's very useful to start thinking in terms of these using machine learning type techniques. There have been some prior explorations that are in the more linear nature. That is, you're solving linear inequalities, and then you can use semi-definite linear programming. But these authors have tried to go beyond that, and they built very small custom networks. Each of these networks is maybe 6 layers or something. And essentially what you're doing is you're building a complicated model for a function, and you have constraints that you can implement in the form of a loss function. And so then it's clear that having this wide variety of functions can help you get very close to satisfying various constraints and let you explore various parameters in theories. There's a similar bootstrap that applies not to theories with massive particles that scatter off each other like this, but for conformal field theories, where the theory looks the same at every scale, and the more relevant parameters are what are called operator anomalous dimensions. So there's a similar, for the 4-point function in this theory, there's a similar set of analyticity, crossing, and unitarity type constraints. And you have other handles too that you know mathematically how to write a linear combination, the answer in terms of simpler known quantities. So this is another area where people have started to explore AI techniques and reinforcement learning for doing cheap high-dimensional searches for what's allowed and what's not in the space of scaling dimensions and what are called the OPE coefficients. So now I want to switch from one set of examples where the bounds are very rich and it's a great avenue for using these methods to another area where maybe there are some more different types of applications, and that is at the Large Hadron Collider, where the Higgs boson was discovered. And that gives us our most direct probe of new physics. So it's essential that we make this very expensive physics experiment as profitable as possible. And this device slams protons into each other, which are bags of quarks and gluons. And most of the time, what happens is they scatter off each other and produce other quarks and gluons, which materialize like these jets of particles. And these form the backgrounds to searches for more rare types of particles, such as the Higgs boson. And then the measurements that are done at the LHC, almost every interpretation of or extraction of a fundamental parameter or measurement of something predicted by the standard model requires you to sort of unravel these QCD contributions. And in fact, you need to do higher order computations in the strong coupling in order to make the most incisive confrontation between experiment and theory. So a typical LHC collision is truly a mess. And here are the two protons coming in. And here's an interpretation of the collision at short distances in terms of quarks and gluons. But as they emerge, they give you collimated showers of things, quarks and gluons, which then get transmuted or change into hadrons, strongly interacting particles like pions and kaons and so on. And this part is the part that's very hard to describe so far because it involves strong coupling dynamics where we have lattice simulations, but as Nathaniel mentioned, we basically can't put more than about 3 particles on the lattice at a time. And you have hundreds going on here, which makes it a very difficult problem. Now, there are ways, though, by measuring only certain things that focus on the short distance, that then you can make things calculable. So whenever we have a process which has a short distance part to it, we can expand it in the strong coupling. And now it just becomes a computational task and somehow to develop and compute the various terms in this expansion. So this is an example of how far you need to go to get precision adequate to meet the needs of the LHC. And this is a plot of the production cross-section for the Higgs boson through its dominant channel, the fusion of 2 gluons. And down here in green, you can see the leading term in the approximation. So if that's all we had, we would have new physics. Unfortunately, we have higher order corrections. And so we end up in this situation here, where now the uncertainty on this prediction is smaller than the experimental error bars, but these are going to go down in the next, after the long shutdown in the high luminosity LHC. And so it would be great to further check the stability of this for, say, going to 1 more order. But this was already a huge task. And just to give you an idea of the task, there are these building blocks that you need to compute. And these are quantum amplitudes, or actually interferences of amplitude on the left of this cut with a conjugate amplitude on the right to make the probability. But when you ask for producing a Higgs, the most stable thing you can do is look for the Higgs and nothing else. And that means you have to allow for other jets and gluons and quarks to be produced. And so you end up getting these kinds of representative Feynman diagrams or topologies that you have to include, and many more corrections to that. But the quantities, like on the left side of these lines, are the building blocks, and we call them scattering amplitudes. And the state of the art for this particular case was 2 loops, and recently went to 3 loops this past year. So this is a list of measurements from the Atlas collaboration of standard model processes. And there's a lot of focus on the Higgs because it's a relatively new particle. And so I mentioned this prediction of the Higgs production cross-section. However, there are many other measurements, and we don't actually know if there's going to be new physics, which channel it's going to show up in. So all of these need improvements. And you can kind of understand where the biggest theory needs are by looking at the gray bars, which are the theoretical uncertainties. And you can see that they're worse where you have complicated final states. Now, in general, there are different routes to perturbative amplitudes. Feynman gave an instruction which pretty much works in any perturbative theory. And there are a set of rules that associate with each graph a Feynman term in the amplitude. And there's a set of rules that allow you to build something we call the integrand, the loop integrand for that diagram. But there are momenta for unseen virtual particles that we have to integrate over. And so we go from some integrand, which is a rational function, to some contribution of a diagram called A sub I, which is a very complicated mathematical function. And then we have to add them all up. There are other ways to do this too. For example, you could evaluate certain unitarity cuts and construct a more global object, an integrand I, but then you still need to integrate this, and you end up repeating very similar tasks to down here. And then you get the same amplitude back, just organized in a little bit different way. In some special cases, which I've been exploring for the last decade or so, there's an alternate route where we do something called the bootstrap. We have enough information about the process that we can just guess what the answer is as a sum of some known functions and some unknown constants. And we have enough constraints, which are constraints on this amplitude, and therefore they are linear equations in the CM, that we can solve them for a unique solution, and we get some specific rational numbers here. So that's another way to proceed, which works best so far in special theories, and we haven't been able yet to use it too much in more general cases. Whereas this method is very general and powerful. But there's a step here where over here you need to solve a large system of linear equations. Over here you need to perform loop integrations. But the technique we have for performing these loop integrations is actually to transform the system into a large set of linear equations. So there's a sense in which the problems here are actually kind of similar. So I just want to illustrate that briefly with one sample integral. So if you wanted to do jet production at the LHC next to leading order, you would need to evaluate this particular integral. So you might have 2 gluons coming in and 2 gluons coming out, and then they would exchange 3 gluons, and you can see there's 2 closed loops in this diagram. And we have to integrate over the momenta of these 2 closed loops. So we do it in a dimension which is close to 4, but not quite 4, in order to make the answer regularized, finite. And these integrals here, the established technique for doing it is to consider instead as something that is a 0. It's a total derivative and no boundary contribution. It's a derivative with respect to the loop momentum, which could be either P or Q here, left loop or right loop. And then in the numerator, you're allowed to put various things, P, mu, Q, mu, or any one of the 3 independent KIs. So there's like 5 choices here and 2 here, so you get 10 equations. There's also a few other equations you might consider too from Lorentz invariance. But the point is that we've enlarged this space by considering not just propagators at p squareds. This p squared is called a propagator and appears with 1 power of the denominator. But we want to enlarge the space to have arbitrary integer powers for these denominators. And if you work out what this differential does, it changes the power because these p's depend on p and q from the routing of the momenta around the diagram. So they shift these powers here. And so what we get is a set of equations which shift the powers by usually about plus or minus 1. So what I'm trying to represent in this graph is a big lattice, 7-dimensional lattice, 3 of which dimensions are shown here. And these green points are different integrals that are coupled together by a given linear equation. So we have an infinite number of equations because these nus could be anything you want. But we only end up with a finite number of integrals that are independent, called master integrals. And we know from experience that we only need a finite number of these to solve the problem. But we don't know what's the best finite number and how to solve that. So in general, this is a multivariate problem where everything depends on the kinematics. But it's impractical to solve it at first that way. So we freeze all the kinematics so they give us rational values entering these linear equations. And then, to avoid the blow-up of very large rational denominators, we map to a prime field for some prime p. We solve the system by Gaussian elimination, and then we reconstruct the rational answer. Usually, you need to use lots of primes because you don't want this prime to be too big for computational reasons. Anyway, you can do this, and you can repeat for many kinematic points and use some tricks to do the reconstruction, but it's still very expensive. And I would say in the precision computation for colliders, there's like two very expensive phases, and one of them is this. And this is getting out the multi-loop amplitudes. There's also another one for doing importance sampling or Monte Carlo integrations that's also very expensive. So there's some premium placed on trying to do this better. And because there's an infinite set of equations, you then ask, how should we pick the best finite set computationally? And there are the notion of seeds. Roughly speaking, in this grid here, all these equations look almost the same, but you can repeat them anywhere in the space, translate this. So that gives you the infinite number of possibilities, but then you want to pick a finite number of seeds, and what are the best sets of seeds? So people have been using genetic algorithms and fund search and reinforcement learning to try to optimize some of these issues, but there's still a long ways to go. So another thing is to try to look for maybe simpler problems where we can push much further and look for much more theoretical data. And this comes from the understanding that in many cases, the simplicity of the amplitudes is much greater than you would have expected by looking at every individual Feynman diagram. So this is an example of the scattering of multiple gluons, which could be written as a sum over tree graphs. And after summing up all of those, and if you choose a bad way of doing it, each individual diagram might be non-zero, but the sum of all the diagrams ends up being 0 for particular choices of the external helicities, when all of them are plus or when just one of them is minus. And then you find the celebrated Park-Taylor amplitudes in the first non-vanishing case for pure gluon amplitudes where 2 gluon helicities are minus. So you get these very simple expressions and nothing simpler than 0. And they're the result of combining many types of diagrams which don't have this kind of simplicity. And so there was sort of a new way to look at how to do these perturbative scattering amplitudes by thinking about them more holistically and not looking at the Feynman diagrams. And one approach involves analyticity, which basically means cruising around in the space of the kinematics until you find regions where the amplitude simplifies. So this is a region where, as you adjust the kinematics, the amplitude is really 2 separate amplitudes just connected by a single massless particle that propagates for a long time. This picture essentially gives rise to new ways of thinking about amplitudes, which are now over 20 years old, the BCFW recursion relations. By implementing those recursion relations, you find that all the tree amplitudes are built from very simple objects. This is the 3-point amplitude with complex kinematics, because the real kinematics in this case are too singular. And in contrast to Feynman vertices, it's an on-shell, completely physical object. So this on-shell recursion, it kind of recurses off of this and generates much more compact formula for trees than were known before. You can do the same thing at the loop level, and that's related to something called the unitarity method. You can also build all loop BCFW recursion relations for these integrands, these I sub i's that I was mentioning. And this form of the integrand, when described in certain variables that live on Grassmannians, led to a different kind of formulation called the amplituhedron that was developed by Nima Arkani Hamed and Yara Trinka. And so this is a reformulation of a theory we know and love from a local Lagrangian that has causality manifest that is in terms of something much more geometric. So different principles lead to describing this theory that do not involve Lagrangians, but instead geometrical principles. So this is an example where a chain of ideas has led to a new formulation. And so the question is, can AI help to find other reformulations that explain Yang-Mills physics from different perspectives, possibly pointing beyond the standard model? So in the rest of the talk, I'd like to tell you a little bit about a program I've been working on with Kyle and the other individuals here right now. And essentially, we found that there's a set of problems in high energy physics where the answers can be phrased as language. And in some cases, we have billions of words or sentences to try to understand. And we also have a situation where we can construct the answers. And the answers are a sequence in the loop order. And we would love to be able to go to even higher loops where we could find even more patterns. And the answer is the solution to a large system of linear equations. And by the time you get to the last loop that we're at, which is about 8 loops, it gets to be kind of hard to generate these equations, but it's much easier to evaluate the equations on a candidate solution. So if an AI oracle tells us what it thinks the answer is, it's quite easy to check it. We have trained some transformer models that are very small compared to LLMs, but have a similar kind of architecture. And those models can predict many properties of the answer when part of it's provided. But we have to provide a large part of it. What we would like to do in the next phase is to use similar models to be able to predict unknown answers. And some of this was probably related to finding new explicit patterns in the data. If we find an AI oracle can get the unknown answers and we can verify it, maybe we don't care so much how it got there. But of course, it's much more interesting to have some more symbolic or analytic understanding of what's going on. And just to say briefly, what are the objects that we're looking at? We're looking at functions of kinematic variables. So we might have a Higgs that's being produced by the fusion of 2 gluons with 1 gluon coming off here. And this is a typical kind of integral we need to do. At 1 loop, we have to integrate over 1 loop momentum. And it's almost a textbook exercise. It gives you some functions called dilogarithms, which are just single integrals of a logarithm. Or you could think of it as 2 integrals of a rational function, an iterated integral. And this is called weight 2 for 2 integrations. So this is sort of the prototype of the kinds of functions that we end up looking at. But they get much more complicated. And when we go to L loops, instead of just these classical dilogarithms, we get special functions which have up to 2L integrations. So we call them weight 2L. So at 8 loops, we get 16 different integrations. And it can be defined iteratively. And the integration always involves a dt over t minus something. And these depend on the external parameters. Well, these are pretty intricate functions. They can be understood very systematically. And the one downfall is that we don't know in advance what they are for a given process. And so there's been a systematic working up to more and more complicated processes. And some of that knowledge involves precisely these integration by parts identities, which also tell you what differential equations these functions obey. And so the sort of state of the art for QCD is that if you want a 2 goes to 2 process with either 0 or 1 external mass, the external mass could be the Higgs, for example, like I showed before, or a W or a Z. Those are roughly at 3 loops state of the art. If you want to do 2 going to 4, the state of the art is around 2 loops right now. And 2 goes to 3 can be done at 2 loops with 1 or 2 external masses. So this is kind of an indication of where the computational limits are right now. These multiple polylogs, which I showed before, we can also understand them in a more differential way instead of an integral way. And they have this property that the functions are always sums of lower weight transcendental functions, 1 weight lower, times d logs. That's the differential. And these are very well organized into as specific objects that belong to something called the symbol alphabet. By taking derivatives, it's actually very similar to reading off letters of DNA, except instead of 4 base pairs, we have a variable number of letters depending on the process. Could be 6, 9, 42, 88. Anyway, we have a variable number of letters, but the basic idea is each time you take a derivative, you kind of expose the letters at the end of the string, and then you keep doing it 2L times until you're done. And when you're done, you end up with a tensor, which involves these letters. These should probably have logarithms in front of them, but we just drop the logs so we don't write them everywhere. And then in front is a multi-index tensor that is a set of rational numbers. Now we started studying this in a particular theory called planar n equals 4 super Yang-Mills, and we found that all these rational numbers were actually integers. And the fact that they're integers, we don't have any proof of that, but it means that we can sort of tokenize things much easier because they're more constrained, and they're bounded in a particular way too. So we can turn them into tokens, and then these letters are already called letters, so it looks just like language. Just to indicate how far we can go, I mentioned in the QCD, the real world, say, we can go to 3 loops for this process with 2 gluons and a Higgs plus a gluon, at least in a large NC limit, and pretty soon any NC probably. But in this toy model we've been playing with, we can get to 8 loops. And so we have a large amount of data. Also, these 2 theories are not as disjoint as you might think. If we look at the weight 2L part of this answer, so that's a pretty complicated weight 6 function, it agrees precisely with the corresponding 3-loop answer over on the n equals 4 side. There's an alphabet that has 6 letters. Doesn't really matter too much how they depend on the underlying variables, but we have, through trial and error, found a good set of letters, which we call A, B, C, D, E, F. And then when we write the 1 and 2 loop answers in terms of these letters, we get these tensors with 2 indices, or 2 letters in a row at 1 loop, 4 letters in a row at 2 loops, and so on. And then they have integers in front of them. At this order, we only see 2 different integers because there's a dihedral symmetry that relates all of the terms multiplying each of these integers. So we have lots of constraints, and so we can actually solve this problem through 8 loops. And if we count how many terms there are in the symbol, you can see it's growing rather rapidly. I don't know, factor of 30 or 20 or 30 with each order. So it's not advisable to look at the full symbol directly without eye protection, but a great place to try to mine some data. And again, the word length, which drives some of this growth, is 2L. And all these coefficients are integers. We have lots of patterns that we understand physically, but we have even more patterns that we found already that we don't understand. And we would love to find even more patterns because we think there are many more. For example, the start of the symbol, you can only use 3 of the letters. And that we understand, and it's related to causality or where branch cuts can show up. But many patterns we don't understand. This pattern is particularly bizarre. this symbol for this process I was just showing, it turns out to be exactly the same as the symbol for another process. And that process doesn't have this operator or this Higgs. It has 6 gluons, particular helicity. And you take the answer here and you write it backwards and relabel the letters in a particular way, and you get this answer. And we've checked this through 8 loops, but we have no idea why it happens. So we would love to find other surprises within the data. And of course, if those patterns can be used to find new principles or predict the next loop order, that would be great. I mentioned that we have a large number of constraints that we can solve. This is just one example. The function has to be a function, which means that its double differential vanishes, and that turns out to imply a bunch of constraints that look something like this. Each of these equations is really a multitude of equations because it only shows the letters in 2 adjacent slots in the symbol. For example, this first equation is really this much longer equation where you're allowed to take any choice of these letters, the 2L minus 2 letters that are not in that pair of slots, and then you specify 2 of them to A, B, B, A, and so on. So we have this large set of linear equations. Those are homogeneous. We also have some inhomogeneous relations that are needed as well to fix the whole thing. But we have a large number of relations, thanks to our friends in the quantum integrability community, to fix and validate any symbol. So you could view this as a challenge to the AI community to help solve this problem. We've been working on it, but we're not done yet. We have these transformer models that have this particular architecture, which I will skip through. The only thing I want to mention is that besides the letters as tokens, the 6 letters, these integers, we tokenize them by putting in an overall sign as a separate token, and then the magnitude in base 1,000. So we might get several tokens if the thing is 1 billion or larger in magnitude. And so our first exercise was to try to train the answer. In this case, I think it was at 6 loops. And we gave it maybe 1 million terms out of the 5 million terms. And the task was by telling it the associations between the integer coefficients and the letters, ask it to predict the integers in a held out set. And we minimize a cross entropy between the model's current distribution and the training set. And so you can get very high accuracy after 200 epochs. The one curious thing about the dynamics is that the learning goes in 2 phases. It gets about half of the coefficients right here. And if you go look, the magnitudes are basically all right, but the sign is being guessed randomly, and it seems to want to oscillate from all one sign to all the other sign. The final answer, which is correct, has about a 50-50 distribution of plus and minus signs. So this is a little bit bizarre thing that we don't completely understand. Another thing would be to try to use AI to predict the analytic behavior of sequences. Since we have 8 loops worth of data, we can go in there and look at some of these integers. For example, if we have an A followed by 2L minus 1 Fs, and we change the loop order L, we go from -2 to 8 to -96 to 1920. And well, Terence has already figured out that this is the coefficient, the double factorial shown here. But then we could check it with 7 and 8 loops. So we were able to deduce this pattern without too much trouble. And then go on, and using this as sort of a base, we found hundreds of similar sequences. This was not done with AI. This was done with HI. And they always have polynomials followed by double factorials and some powers of 2. And this polynomial goes up to cubic. And it's limited. We're limited to strings of length 8 because beyond that, the polynomial has too many unknown parameters, and we don't have enough to fix it completely. We've recast these exact formulas into more recursive looking formulas in some cases, but we're still trying to understand these patterns in a better way. And this seems like a case where some agentic AI could be very useful. And we would like to find many more of these sequences. In one case, which was a success for using an AI model, there's a model called PySR, developed by Miles Kramer, no relation to Kyle Kramer, as far as I know. So Matthias Wilhelm was using this, which involves various genetic algorithms to develop Ansätze, and it did determine some sequences that we humans were embarrassed that we had failed to find. And although it tried many options, the solution was simply to put a power of 2 to the 2L between two different polynomials, and then that solved a few of these sequences. So we think based on this, there's lots of more room to find and try to understand many more of these specific patterns. So in the next phase, we're going to try to train the models without telling it more than we really know at that loop order, should know. And we're also going to work on more compressed forms, try to incorporate all of this seed data, and look for more seeds. And we're also looking at just more efficient ways to solve the too many linear equations. So there are various ways to streamline the way we had been proceeding before and make more use of the structure that we're seeing. Now, I was mentioning one specific process, but there's at least 4 or 5 processes that are known to a high enough order that you could really do a lot of data mining on that. And these are all in planar n equals 4 because it's a much simpler theory. So we would love to know if this can be utilized across various quantities in this theory. And then, of course, the real challenge would be to try to go back to QCD and apply it there. And this is definitely a much bigger challenge because there are rational prefactors that have to be taken into account. But I see I've really used up my time, so I will stop here. Thanks.